Hi everyone! So today I'm going to be talking about the birth of stars, and depending on if I have time at the end, I can give a little insight of what goes beyond just the birth and the start of the star. So I'm going to jump in just so I can preserve some time, but if you have any questions, then just put it in the comment section and I'll try my best to answer it. So to start, every star comes from hydrogen, right? So just to conceptualize this, I'll just draw, but it's really not to scale, so don't take this to heart. So everything starts with a huge hydrogen cloud that has a lot of mass in it and a bunch of distance in between each particle. Gravity eventually touches this cloud and makes them move together or condense into a center of mass. So by this time they're getting a little closer. And because these particles are getting closer, they're holding more potential to run into each other and have an interaction. So because of those things, it's going to create an energy that brings about higher temperatures. So right here, the temperatures are increasing, right? Beyond this, it gets a bit more denser into a smaller area and then getting hotter from more interaction. So it's like super condensed right around here. And around this time is when it hits around 10 million Kelvin, which is the temperature at which hydrogen fusion starts. So traditionally, when we see the Coulomb forces and the electromagnetic forces, right, they tell us that a positive and a positive cannot attract, they repel. Same with a negative and another negative, they repel. But what we do know is that a positive and a negative, they attract. However, since it's at 10 million Kelvin, around this time, this makes zero sense. So just to give you a little insight of what hydrogen fusion looks like, right? In this cloud, we're just gonna pick two of these guys right here. So a hydrogen atom looks like this, right? You got a positive in the center and then a negative on the outside outer shell. And then we're going to take the other one over here too. And what these tell us is that they're never going to interact with each other. In fact, they're going to push each other away. But the forces over here are so strong that eventually they push together and fuse into a single atom. And what that atom ends up looking like is like this. But instead of having two protons put into the nuclei, actually one of them turns into a neutron. And this is what is known as deuterium, which is a heavier version of hydrogen, basically. So this right here is deuterium. Heavy hydrogen. And then eventually, this would end up turning into helium with more energy and more fusion over here. It just ends up turning into this. So then you get two protons and two neutrons in the center instead of just this. So the hydrogen fusion is the combination of the nuclei, like I just demonstrated here, which makes the density smaller in the atom because now you have one instead of two. But the energy expels outward to balance the inward pressure of what is happening with the atom collapsing. So this is why it doesn't collapse any further than deuterium, because it's controlled. There's outer forces going on while these ones went in. So by this point, when there's helium inside, so now this cloud of hydrogen turns into a cloud of helium, this is what is known as a main sequence star. Main sequence star. Now the main sequence star is the start base of the rest of the other stars and giants. For example, we have the red giants, which basically the red giants change from hydrogen fusion to Okay, so red giants, right? Red giants, they start with the main sequence star, where hydrogen fusion only happens in the center. And then you have the outward forces of the star that keep it inside, right? But eventually it starts making more of hydrogen to the point where it only happens in the core, and then there's an outside shell of helium that moves into the core, right? And that's when energy can leave because it's being expelled, but it's also going inward because the hydrogen is going in there. And at this point, you can see that the star is growing in radius, but it's called a red giant because there's more surface area on the outside that allows cooling to happen. Because the only, like this right here would be hotter than this because it's a pure center of energy. But here, it's a pure center of energy with an outside that kind of dissipates the temperature release. And that was just like a brief introduction to red giants, but then there's also white and black dwarfs, which again, we start with the main sequence star. And then we move on to the red giant, knowing where the red giant stands. And then we go to a whole new fusion where it hits around like 100 million Kelvin. And at this point, there's going to be a really dense center of oxygen and carbon. And then you have the helium right here. And then you have the hydrogen fusion shell. And then right beyond that, just on the very outside, you're going to get hydrogen plasma. And this core explodes with a helium flash, and it makes a higher volume of the star. But the white dwarf is when you can see light from this, and then the black dwarf is when you can't. The denser core is not hot enough to move on to the next stage, so that would be the black dwarf. But keeping this in mind, eventually the hydrogen and helium will run out, and that's when a star potentially dies. There are also some potential stars that have never made it past the hydrogen fusion part, like Jupiter. Jupiter never made helium, so it never became a star. But an overall conclusion, just because I'm running out of time, the fusion can keep going up until iron. So we started with the hydrogen outside, right? And then it turned into helium, and then it can turn into carbon, and then it'll turn to neon, and then it'll be oxygen, then silicon, and then iron. But the thing about iron at this point is that it doesn't give off any energy, so at this point the star would be endothermic. But these are the potentials of different fusions and different levels of stars and what their lives look like. But now that you know the basic main sequence star idea, you can take this and learn the resources and expand a little further about the lifespan of stars and the different types of stars. But yeah, the birth of stars all starts with main sequence, which is just the basic hydrogen to helium fusion. Thank you, everyone, and let me know if you have any questions.